redundant.
Yeah, I can
So,
see your screen. Yeah.
Okay. And everyone, of course, I'm sure you're aware that we do have a code of conduct. Is that something you would like to speak to, Alpha?
Yeah, I can start it. Hi all, welcome to our session, GroupBy 2021. This session is for everyone who like to learn something new about data. It's for community by community. And we have a 2-day session, today and tomorrow. So you can join on the session as well. So I'm moderating this session, and its session is about SQL Server internal and architecture for developer by Kevin. And Kevin is very expert in data, and he has presented a lot of sessions in a lot of conference in many different countries. And he liked to read sci-fi books, and he liked to travel. So Kevin, floor is yours.
Also, just a word of thanks to all of the sponsors. Of course, I am a representative of SolarWinds. We also have some great content and material coming out from Redgate these days. And if you haven't already availed yourself of the conference, the organization known as PASS, the Professional Association for SQL Server. So check out pass.org. And next month is the big PASS Summit. I was one of the founders of PASS back in 1998, 1999, and I was president for 4 years. So I'm always going to be a big supporter of PASS. Also, we have some great sponsors like SQL Solutions Group, Randy White, Wayne Sheffield, Jason Brimhall, and other great Microsoft certified masters, all consultants there for that organization. Minionware, also run by some friends of mine, Jen and Sean McGowan. So some great sponsors, and I hope you'll patronize them, not only because I am a sponsor, but also because they contribute enormously to the community. They build great tools that help make our lives better. And so, it's important that we interact with them as well. Now, let me open up my slide deck. Take just a moment, if you please. Now, this particular session is actually probably more like, an hour and 15 minutes, but we only have 45 minutes. So, and we're a couple minutes into the presentation already, right? But I'm gonna have to strategically skip a couple of the longer explanations, but my hope is that you'll get a good idea of what the internals are for SQL Server and the major components of SQL Server. It's this area here of our agenda that I probably won't be able to go into full details on. So thread management, query optimizer, I'll be able to give you an overview of those things, but we may not be able to dive super deep in those because I'm sure you want to get to the next session and see all the good stuff happening. So what's the premise of our session here, where we're going into the insides of SQL Server? Why is that significant? Well, what we have is a situation I find very frequently where many of the people that I interview for senior level jobs as SQL Server technologists, it turns out that they really don't have a very deep understanding of how SQL Server works. A lot of the things that they know and they do are kind of learned by rote, R-O-T-E. So they don't know why it operates the way it does. And this is a pretty big deal because this is a fundamental aspect of our role as IT professionals. If you're a farmer, you should know about plant metabolism and their relationship to the environment and to weather, their life cycle, the best time to harvest, the best time to plant. If, let's say you have the dream job of working on a Formula One pit crew, you may only be responsible for changing out the tires as fast as you possibly can when that Formula One race car comes into the pit stop. But you sure as heck better know what an internal combustion engine is, how it works, its major components, what the braking system is, what the those kind of things. True professionals know all the internals of what it is that they work with. And the reason for that is it makes everything else they do in that role better and more successful. And so this is the same for you. As a database professional, you need to know these things. And I'm surprised how many times I meet people who say they are, talented SQL Server, senior executive, or, senior DBAs, senior developers, and yet they don't know what the checkpoint does. Okay. That's one of the most simple and most direct of internal processes, which we will talk about today. So this session contains a lot of things that I would ask you in an interview, a technical interview, if you were to tell me you were a senior technologist in this area of skill. So let's dive into that. The first thing, though, that I would like to do is to set context, right? So why do relational databases work the way they do and give us all the problems that they do, right? Well, relational databases didn't come out of thin air. They were designed by a group of people who were trying to fix some of these crazy problems that we were having with the preceding era of database technology. So the preceding era of database technology was primarily mainframe based. Some of it was on mini computers like VAX VMS, which is one of my favorite computer systems. And so, when we have a big mainframe and the banks and so forth that ran them, in fact, even in those days, we called our profession EDP, not IT. Back then, it was electronic data processing, which basically meant let's do the stuff that the accountants do. Let's do the stuff that scientists do, but really fast, right? Let's just crunch a bunch of numbers, process a lot of checks really fast. So we weren't even concerned with information at the time. It was just data. And a lot of us know the difference between data and information. With relational databases, we needed to counteract all of the shortcomings and weaknesses of these mainframe batch-driven approaches. And so the theorists, and I'm blessed that I got to meet several of these people, Dr. Jim Gray, for example. They've decided that we're going to use an acronym to represent all these good characteristics of a relational database. And this applies not just to SQL Server, it also applies to Oracle, MySQL, PostgreSQL, SAP, HANA, all of the big databases out there, relational databases. And it's the acid property of transactions. It's not, as I have on the screen here, it's not the hydrochloric acid, sulfuric acid, or lysergic acid, or anything like that. It's an acronym. And A, in this case, stands for atomic. So compared to the old days, you could both change data and insert data with a single set of COBOL statements, things like that. Whereas today, with our relational databases, we have a high degree of atomicity, which means each statement does one and only one thing. So a select only reads data. A insert only puts new data into the database, and so forth. So the idea is, in chemistry, if you took a compound and broke it down into like my coffee cup, and then you broke it down into molecules, like caffeine, my favorite molecule, and then you broke it down to atoms, that's the smallest unit of measurement at which everything has distinctive characteristics. If you go smaller than atoms, well, a proton from a carbon or a nitrogen atom is still just a proton. It's lost its unique characteristics. So that's one thing we needed, because it made it so hard to troubleshoot and to debug problems on the mainframe. We have to bring in atomicity so that we can fix stuff. The next important acronym that we have is C, for consistency. And believe it or not, there was a time where you could write the exact same code with the exact same parameters, and it might execute differently on Wednesday than it does on Thursday. And that is something that we can't abide, right? We have to make sure that when a transaction performs its prescribed invocation, that it does exactly the same thing every time and that the results are reliable and predictable. I can't imagine going to an ATM and asking for $100 from the cash machine and it's like, how about $103? Okay, that sounds good. But then on a different day, how about $97? No, I don't like that. The next and very important characteristic is isolation. So in my case, I have one son and 6 daughters. And at one time, 4 of them were going to the university at the same time. And so we had a kind of a pocket money account that they could all use, take their cash card to the cash machine. And if we were running in the day, those cash machines in the days of these COBOL-based mainframes, it would be possible for 3 of my kids to go to the cash machine at exactly 12:11 p.m. And even though there's only $100 in the account, each one could type in their number, ask for $100, and then all 3 of them would get $100. And it wouldn't be until the night batch processing that I would find out that I was being charged multiple overdraft fees. Okay. Now today, what happens is the first person who gets there, so Savannah gets there first, she starts to withdraw that $100. That set of records is exclusively locked so that she can complete her transaction in isolation of everyone else out there. That was a major innovation at the time. Today, we think of it as, oh, that's table stakes. You can't process data without locking the records that you need access to, or providing another method of concurrency control. But yeah, in the old days, that might not happen. And then finally, the last and most important characteristic of transactions on a relational database is that they must be durable. And so as an example, if I was going to that cash machine in the days of COBOL, put in my card, and behind the scenes, this taking out of $100 is actually 2 transactions. One transaction deducts $100 from my account, and the other transaction says, here is $100 for Kevin, and it causes the cash to be spit out. But what happens if lightning hits the transformer running the cash machine and it breaks in midstream? Well, in the old days, it would have deducted $100 from my account, but it would never have gotten to that next part in which it put $100 in my hand. And I would be very angry about that. Nowadays, what happens is either the entire thing happens, both of those 2 transactions in a single batch, either they are both completely committed to the database, or they are rolled back as if they never happened at all. And this is extremely powerful. It is also, if you pay attention here, each one of these is a little bit more overhead on the database system, okay? So having a good transaction log system takes a lot of extra work. Atomic and consistent, those aren't that big of a deal. That's really the parser and binding and simplification, those early kind of easy steps in the process of executing a transaction. Isolation is the entire locking engine. So that has a lot of overhead and a lot of potential to slow things down. People lock transactions and records too long. And then durability is a big deal. It takes a lot of overhead. When MySQL first came out in the late 90s, early 2000s, a lot of people praised it for its speed. It just didn't have a transaction log of any kind. Now note, to provide durability to a relational database, you don't have to do what SQL Server did with a single transaction log. For example, Oracle divides that functionality into 2 components. They have an archive log and a redo log, but they meet the functional specification for durability there. There's also components inside a SQL Server that are there over and above the ACID properties of transactions and the kind of rules for relational databases. So there's components in there just to provide speed and scalability and performance. Things like the way the caches of different sorts work, which we'll dive into. There's also things inside of SQL Server to maximize the capabilities of the hardware. And at different eras of hardware, there were different things inside the architecture of SQL Server that could help make it faster. And then finally, maybe there's something cool that Oracle or MongoDB or one of the big players that are competing with Microsoft do. So they do put in things specifically to fend off a competitive threat, if you will. Now, depending on your experience and your background, you may have heard a lot about or even worked with NoSQL systems. And it doesn't strictly mean no SQL language. It means not only SQL. So most all of the really good NoSQL databases actually support the ANSI SQL, probably the 87 or the ANSI SQL 99, one of the older but kind of basic standards of support. But keep in mind that none of those databases are designed for ACID properties of transactions. If you need secure and reliable transactions, there's nothing better than a relational database. And I'll die on that hill if you ever want to argue about it. Non-relational, these NoSQL database systems were developed in the mid-2000s in support of social media, the first of which was Hadoop, built by Yahoo. But then we've got other things like Cassandra and MongoDB and so forth. And they are all based on something called the Cap Theorem. So what the Cap Theorem says is you've got three main capabilities we're going to provide: consistency of the transactions, availability of the database, and partitionability, meaning the number of server nodes we can spread it across. So for example, Google, I think, uses over 5,000 server nodes for one of their big shards. So you can have consistency, availability, and partitionability, but you only get to have two of those three. And again, think about it. If you're posting on a social media platform, cute picture of your kitty cat for your grandmother who lives on the opposite side of the country than you, it doesn't matter if it's, takes 20 minutes for it to reach consistency. They call that eventual consistency. But if it's money, you need to be consistent everywhere anyone might access information about that money. And so they have entirely different sweet spots. So I am also cautioning you that don't believe anybody who says this NoSQL database can do everything that this relational database can do and more. It's not true. What is true is that NoSQL databases have some things that they are especially good at, and relational databases have some things they're especially good at. So let's get inside the database. And the way I decided to do this was to try and tell a little bit of a story rather than just inundate you with facts and details about how the internals of SQL Server work. And so what we have here is a neighborhood, okay? And it's like, imagine Sheldon is going to a conference in Manhattan, right? And if he walks outside of the hotel over here, and he walks down the street to go to the conference center, he's going to see all kinds of little small structures as he walks down the street. He's going to see a small machine he can drop a quarter into and open it up, and he can pull out a newspaper. He's going to see a vending machine he can buy a soda from. As he turns the corner here, the buildings get a little bit bigger. And so they're still very fast and easy to interact with. You can buy newspapers from the newspaper man and get a candy bar and a soda, but you haven't actually entered a building or anything like that. But then when you finally turn the corner down here to access methods and transaction methods, these are really big walk-up buildings, 5-floor buildings. And if he wants to do something in there, chances are he's going to have to go up a lot of stairs. It's heavy work. And then here in the center, we have these two big high rises, actually three, you could say. On the left-hand side, we have the transaction log. We have the database files. Usually you should have multiple database files. And then we also have memory from the server and by inheritance down into SQL Server itself. So these are big, 70-story, 90-story buildings. And every time we interact with these, that's where it gets really expensive, okay? So Sheldon walks out of the building. And in this case, in our analogy, Sheldon is actually a query, right? So, and it works the same, no matter if you're on a web portal querying back to a database, you're on Azure SQL database on the portal, you're on a client server application, or even on the terminal that is connected directly to the SQL Server itself. So what happens is, oh, and by the way, I kind of organize these by a little bit by color. Everything across the top and down here over on the right-hand side, these are all steps in the process of executing a query or a transaction, I should say, because it's the same for inserts and updates and such. These are all in the relational engine. So that's one set of code. Whereas at the bottom, what we have is code that is part of the storage engine. And the storage engine is kind of where the rubber meets the road, where all these logical operations turn into physical operations. So Sheldon steps out of his hotel to walk to the conference center. And in that circumstance, really, it would be analogous to we are instantiating our query. And the first thing that happens to instantiate the query, let's say you type in select star from sys.dmos performance counters. That's a DMV that provides information comparable to what you would get from perfmon if you did it straight from the Windows OS. And so you instantiate this query, and SQL Server takes the query and puts it into something called TDS packets, the tabular data stream packets. And it was something invented by Sybase way a long time ago and is inherited in the way SQL Server does its work. Those TDS packets are then something that are easily transported by the SNI that we have labeled here, the SQL Networking Interface. In the old days, the 90s, probably the most common SQL networking interface was name pipes. But in the late 90s and early 2000s, TCP/IP began to be the biggest and most popular, and has since stayed the biggest and most popular. So SQL networking interface grabs those TDS packets and then puts them into the TCP/IP packets, sends them out over the network to the target SQL Server. And SQL Server is listening usually on TCP/IP port 1433. Anybody out there? And when you connect, when Sheldon connects to the database, the component inside of SQL Server called the SQL OS sees the query come in, sees Sheldon interacting, and says, okay, I need to do a few things. First, I'm going to put you on a scheduler. Every CPU in the SQL Server has a scheduler, whether they're physical or hyper-threaded, logical CPUs. And then on that scheduler, I'm going to give you a thread to execute your code. And I'm going to then hand you over to the parser. So what's a parser do? A lot of times when people are asked that question, they say, it parses. Thanks a lot, Captain Obvious. Yeah, it parses. But hey, Blythe.
Hi, sorry, I didn't mean to giggle at you.
This component is sometimes called the algebraizer, or the normalizer. The main thing it does is it validates correct syntax, okay? That's what most people know it to do. It does a little bit more than that, though. So if you have any kind of abstraction like CTEs or views, it expands those out. And it also identifies any of the constants that you have. So if you had a query that had a parameter where hire date is equal to or greater than such and such, it would say, oh, okay, I've got some variables, I've got some constants. Now I know which is which. And then it will take and turn that into a logical parse tree. And throughout this process, what you're going to see is SQL Server wants very much to either, well, it wants very much to save time. And so what's the best way to speed up a query? Well, there's two ways to make a query come to its end quickly. One is, if it's broken, make it break as early as you can in the process, okay? Like if you misspelled something, one of the 600 words in the parser's vocabulary, well, let's break it now, break that query at the parser rather than let it go any further. The second thing is, if you're executing a query and we have to build this big execution plan, wouldn't it be great if we could just reuse one that's very much like what Sheldon is asking us to do right now? So that happens at the parser stage. SQL Server takes a look and it says, is there anything in the plan cache right now that's essentially the same thing as what Sheldon's asking? Maybe the value is different in the where clause, but it's asking for the same columns from the same tables. If there is, well, that's great news, because Sheldon can now shortcut all these other steps to the right, binding and simplification, all that stuff, and go straight to executing the query. If that's not the case, though, then SQL Server has to kind of put that stub, or sometimes called a query thumbprint, into the plan cache, and then go to the next step and start filling in details at each of these steps as we go along. So at the binding step, well, we learned that you had used all the right syntax. We figured that out. But what happens if you don't have permission to the tables and the columns that you referenced? Well, it's at the binding phase that you would get a permissions error. You know, you're selecting against a table you don't have select permissions on. It also would check for things like the basic metadata involved. We're talking only like the table names and the column names. It would look for data type issues. So if you had a union between query A and query B, each ordinal position of the columns you invoke has to have the same data type. So if one was an integer and one was a float, they're both numbers, right? But they're not compatible. So it might give you an error on there. It also looks at any aggregate functions you have. So if you have sum or average, min, max, that kind of thing, count, it makes sure that you have all of the right things in your GroupBy state. And once it figures all that out, it updates the details in the execution plan, and then it goes on to the next step, simplification. I was around when they added the first of the simplification features to SQL Server, and they were really cool. Back in the SQL 6.0, 6.5 days, you could write a query that was a nested correlated subquery. So, basically I want data from these two tables. I want the outer data to be sales order header and the inner data to be sales order detail. Okay, I'll create an execution plan for you. And then you could write the same thing using a join statement, and it would create an entirely different execution plan for you back then. Nowadays, it does a lot of work to convert functionally equivalent operations into the exact same behind the scenes behavior inside the relational engine. So subqueries are rewritten inside of SQL Server behind the scenes as a join. Inner joins get rebuilt as outer joins sometimes. Sometimes you've got a very large query and you didn't realize that you were joining the same tables a couple different times, maybe once in the where clause and in a join clause. So it'll take out all those kind of redundant joins. It'll take care of foreign key join elimination. Another thing that's interesting is that if you have constraints on one of the tables, for example, it says where quantity is between 0 and 100, but it turns out you have a rule check constraint in your database that the quantity can never be less than 0, or it can never be 0. It has to be a certain number and above. Well, that's a contradiction if you're asking for show me all the sales with a quantity of 0. So it would fail at the simplification stage because you're breaking a rule. And that's actually good because, if it goes further into the process of doing this building of the execution plan, it wastes a lot of resources only for it to fail at a later stage, right? So let's do it earlier rather than later. Now, once it's figured out all those different kinds of things, and I have different videos that explain all of these other details you see in the pop-up there, but after it does all these different checks, it updates all of that information here in the plan cache. So it's building the execution plan microsecond by microsecond as it goes along. Updates all of that info, and then it goes to the next phase, which is trivial plan. And so what happens in trivial plan is the optimizer, believe it or not, it still hasn't even looked at what we consider what most query tuning experts think of as the first thing to look at, which is your indexes. All the way up through this point, we haven't looked at indexes at all. And so with a trivial plan, what SQL Server does is it says, how many ways do we have to solve this query? Certain kinds of queries can only be solved in one way. For example, if you have a table that has neither clustered index nor any non-clustered indexes, the only way data can be retrieved from that table is to do a full table scan. Even if you put a where clause in your query, it doesn't matter. It still has to do a full table scan because there's no index to speed up that operation. So if SQL Server encounters a situation where there's only one way to actually do what you are asking it to do, then it creates what's called a trivial plan. A trivial plan, though, is so trivial and fast to make that SQL Server, when it creates the execution plan for the trivial plan, it puts it in the plan cache and marks it as available for immediate eviction. So it can throw it out right away. And so SQL Server never really seems to accumulate a lot of those trivial plans for very long. It's constantly cleaning them out. Now, if it finds that it is a trivial plan, that means, again, SQL Server can say, aha, Sheldon doesn't have to go to all these other buildings. He can take a big shortcut and cut right through to execution of the query. Woohoo! But if that's not the case, it updates all the details in the plan cache, again, in the execution plan, and takes us around the corner of this little Manhattan neighborhood. And then it loads the metadata. And that's not just the indexes. That's not just the statistics. SQL Server can auto-create statistics itself. That's a level deeper, too. Something very important called the histograms. So every index not only tells us like the cardinality estimate, which is the number of records that a particular operation would affect, and it has density, and it has selectivity, and it has some other things that SQL Server keeps track of, but these histograms. And so what that does is across the different segments of the index, let's say it's an index on last name of all our customers. Well, you're going to have a lot of people whose last name starts with R and S. So that they call it a bucket. So that bucket on the index that holds people's last names starting with R or S is going to have thousands of people. On the other hand, the bucket that holds P and Q, there's very few people who have last name of Q, starts with Q. So that bucket might have just a few hundred last names in there, people with a last name of P or Q. So that's what the histogram says. On this particular part of the index, that's how many records exist as we go along. And so histograms are very important as well. So SQL Server loads all of that information in, but it also needs some more information. It needs to know how many CPUs there are. And this is important for parallelism. where it might split a query across multiple CPUs and speed up the processing. It's also important for memory grants. So let's say if all of the records to be retrieved in your query was 16 megabytes, but the server only has 4 gigabytes, SQL Server might give you a stingier memory grant than the 16 megabytes you need, because it knows that it will be kind of churning through different sets of that total 16 megabytes. And so it gets by with a 4 megabyte memory grant because it's kind of shuffling through all of the stuff, only 4 megabytes at a time. So SQL Server tries to be stingy with the amount of memory it hands out. And then we have some other things like your collation and your set options that SQL Server will load in. It grabs all of that information and it loads it into your execution plan. And there's also something behind the scenes called the Memo Structure. And this is something I cover in another presentation I do that goes into really, it's called Query Tuning Internals for the Advanced SQL Developer, where I actually explain how the memo structure works. And so this is where you can see SQL Server considered a nested loop join and it considered a merge join, but the merge join was a lot more expensive. And so it chose to go with a nested loop join. SQL Server also applies a set of features, and this is happening could be happening concurrently even, for that matter, with loading the metadata. So one of the things it does is it loads up all of the tables that might be involved in joins in your query, and it applies some heuristics, and it may decide to reorder the join from what you have specified in your query. So you might have said join table A to B, and then join table B to C. Well, if it turns out that you start with table C, that you can eliminate 100,000 more records very early in the process, well, that's one way it keeps the memory grant down. So why don't we start with table C to A and join there so that we carry hundreds of thousands of less records to the next operation in the execution plan. Once it figures out the join order, again, it updates the parse tree, the memo structure, the execution plan, okay? So it's constantly writing back to the plan cache, putting in all these updates as it figures out the best way to execute this plan. Now, of all of the things that have happened so far, they're all on CPU, retained in memory. They're very fast and transient, but the most resource intensive is where we finally get to the optimization, or the optimizer. And the optimizer isn't actually looking for the very best plan. It's looking for an optimal plan. I always joke that it's like some of my daughter's dating practices. He may not be good, but he's good enough. So same thing there. It may not be the very best execution plan, but it's going to be good enough to satisfy the end user. And there's 3 phases of this optimization. The first is a transactional plan, which is the kind of plan you would use for singleton inserts and updates and deletes in like a data entry application. They're very simple. For example, SQL Server takes a look at the shape of the query you've sent it, and if it has 2 or less tables, it says, oh, okay, maybe I'll do a transactional plan with this one. Quick plan is a little bit more elaborate, but not a lot. So maybe 3 tables. So it just looks at the execution plan shape, 3 tables, they're all joined on the same column throughout, you know, from A to B to C. And so maybe I'll use a quick plan. Once we get to phase 2 for full plan, SQL Server inverts the way it figures out the best plan. So instead of looking at plan shape, now it says, okay, this is pretty complex. So I'm going to open up the book of about 7,000 different cost estimation components of the query optimizer. And now I'm going to look for things I can prune off, because I'm going to go through all kinds of these different costing methods, algorithms. So for example, if your query is against tables that have max data type values, but none of the columns in the set item, select item list, or in the where clause or front. None of those max columns are addressed, varchar max, var binary max. Oh, well, I can clip off that whole set of costing algorithms for things involving max data types. Is there anything in here who uses really deprecated data types like SQL variant or text or image? Nope. Oh, great. I can clip off all of those costing algorithms. Okay, is there anything in here for anti-semi joins? Oh, well, no, we're not doing any of those anti-semi joins, so I can clip off all of those. So it's a way to get to a good enough plan, excuse me, very quickly without actually making you wait forever to find out, the results of your query. So once again, all of that information updated into the plan cache. Okay. Once that happens, now we move to the, and by the way, that plan is a hash of the binary of your, not the actual English text, but the binary. And so if you and your colleague next to you are writing a query that needs to do a lookup, and they write theirs all lowercase, and you write yours where all the keywords are in uppercase, SQL Server won't be able to reuse those execution plans. It's because it sees it at a binary level as different. A lowercase s in select is a binary value that's different from the uppercase s in select. So keep that in mind too. So now we move on to the next part, and this is where the two kinds of operations, reads and writes, this is where they differentiate. So for reads, what happens is SQL Server talks to, Sheldon is walking along, comes up to the access methods building, and the access methods is how SQL Server decides to physically retrieve data for you. So for example, if you have a table that has a clustered index on it, but you don't have an order by statement in your query, well, whatever is cheaper for SQL Server, according to the cost estimate, the access methods will very likely enforce. So for example, it may say, oh, it's not cheaper to actually retrieve this in clustered index order because there's already a really big covering index loaded into the plan cache. So I'm going to use an unordered index seek to get your data. Stuff like that. It's very interesting the way it behaves there. So the access method says, okay, where can I get my data? So, oh, you know what? The first thing I need to do, according to the rules of ACID, is I need to make sure that I'm isolated, but it's only a read transaction. It's only a select state. So that means that when the access methods engage the transaction manager, all it needs to do is to make sure that those records that are needed get a shared lock. And so in order to find those, SQL Server then sends Sheldon to the buffer manager. And the buffer manager has maps and GPS and all kinds of fancy ways to find exactly the records you're asking for, even if that's one record out of a billion. These structures are called, they have a variety of names. The global allocation map, the GAM, the index allocation map, the IAM. If you're looking for free space to insert records, there's something called the PFS, the page free space list. So all of those are constantly kept up to date and tracked in the buffer manager. And so the buffer manager says, aha, I've used my my GPS guidance system to find my way to all the records you need. Now let's issue locks and let's see if those records exist, if they have been loaded already into the data cache. If they have been loaded or are there in the data cache, great. Sheldon gets his shared locks, he's able to read the data, commit his transaction, off he goes. On the other hand, if they're not loaded up into the cache, then SQL Server needs to go to the database files. You should typically have at least 4 database files for your user databases. It will then find all of those records that it needs, and load up all those 8K data pages upon which they sit into the cache, the data cache, and provide that back to Sheldon. So then he moves forward, gets the transaction complete signal. It varies a little bit though with write transactions, and it can be significantly slower, even though you're accessing the exact same columns using the exact same where clause and join conditions as the select statement we just executed. One of the first things you will see is that the execution plan will be a lot bigger in certain circumstances. That's because all of the data is, all of the triggers that exist on any of the tables in your query, well, that logic has to go somewhere. So if it's an insert or an update or a delete, you can have triggers based on those operations, but you can't have a trigger on a select statement. So it can make your plan cache bigger if you have lots of triggers. It can make your execution plans a lot bigger. And then the other thing that a lot of folks forget about is any kind of check constraints or foreign key constraints, okay? So let's say I'm doing a query in AdventureWorks against sales order header, sales order detail. And in sales order header, I have a customer ID and I have the salesperson ID. And I have foreign key constraints on those. Well, in order to make sure I have the customer ID of a real customer, I basically have to select against the IDs of the customer table. And that logic is a select statement, has to go somewhere. So it goes into this plan cache. I have to look up all my salesperson IDs. And so that is a situation where I now do a select against that. And then in the sales order detail, which is joined to sales order header, now I need to make sure that all the products that I put into the list have existing product IDs and so forth. So that's one reason why you'll see comparatively massive execution plans for a write operation compared to the same thing in a select statement that affects the same records. Also, SQL Server has to obey those ACID rules of transactions. So one of the first rules there, and it's a big blocker if you're not paying a lot of attention to performance, is that we have to have a durable transaction. So before any other processing gets done, SQL Server has to write that transaction to the transaction log. And basically, if you have a write-heavy application, your database will never be faster than the transaction log can write transactions. So that happens serially as each end user enters a transaction. It's written one after the other into the transaction log. So it's not serialized or randomized reads and writes. It's serial, one journal entry after the other. On the other hand, once that finishes, and there's a function you can use called fn, DB log, I think, where you can actually convert the non-human readable contents of the transaction log into human readable content. Now SQL Server goes to the buffer manager and says, okay, where can I find the data to complete my update statement or my delete statement? So SQL Server now has to do the same thing it did during the select statement. I have to engage the lock manager. Of course, the locks are much more stringent, right? So it's possible that somebody else has some exclusive locks and Sheldon has to wait 5 minutes until they release it. But in any event, same thing happens as before. The buffer manager has a map to all the transactions and data and so forth. I should say solely. It has a map to all the data, and it says, where can I find this data? Maybe it's already loaded in the data cache, but maybe it's not. And as before, it goes to the data files, loads up any of those 8K data pages that have records on them that need to change, pulls them back into the relational database. And from there, once they are loaded, SQL Server will then start to change all the values on those pages, okay? They are not, however, written to the database files, and it could be quite a while before that happens. These pages are now called dirty pages, meaning they're different in the cache than they are in the database files. So when Sheldon goes to the transaction complete stage, one more thing needs to happen, which is the checkpoint. And the checkpoint happens by default every minute, but every thread can also invoke a checkpoint. So multiple checkpoints could be happening all the time around the clock. Once that checkpoint occurs, that's when these changed pages are written to the disk and made permanent in the database. They may still stay in the cache, but they have been hardened, if you will, to the database file. So, and once that is completed, then Sheldon is able to finally come back with the done in process message and begin his next transaction inside of the SQL Server database engine. So before I go any further, Alpha, how are we doing for time? And do we have any questions so far?
Yeah, I think we have a 2 question and we have 9 minutes.
Okay.
Shall we start question or once you finish?
Go ahead and give me one of the questions if you don't mind.
Okay, yeah, sure. So first question is by Madhu, and she asking why memory grant is shown only for sort and hash. For other queries, how to check how much memory requires?
So this can be seen in several different ways, and that's a great question. The reason it's shown for sort and hash is because it can be so problematic with those operations. Typically, when you have a sort or you have a hash, it has to spill to TempDB. And depending on how big that is, it could take a long time. So that's why it's been easy for you to find that information. However, in Plan Explorer, our free query tuning tool, we show you all that information. You can find it in the XML for the execution plan. And you can also see it if you're looking at the execution plan in Management Studio. If you turn on full information, there's a little, you press F4, pops up a little panel that shows all of the information step by step for all of the different query plan operators. And so you can see as you move through a query at the different operators, how much the memory grant will be. However, that is a feature that is highly dependent on the version of SQL Server you're running on. So there was a big change in SQL Server memory management in SQL Server 2012. So I wouldn't be surprised if you don't get any of that information prior to that. But after that, I think you can see all of it. You just have to go in search of it. All right. Anything else?
Yeah, there is another one again from Madhu, and it's related to parallelism, execution plan for parallelism. So her question is how to relate a cost of threshold parallelism to a cost of operator in an execution plan for parallelism.
You know, unfortunately, I don't think we have time to cover that, Madhu. But the good news is that your next question, how does the Lazywriter work? Let's make time for that because that's my next set of slides. Before in the diagram of the whole set of internal structures inside of SQL Server, you remember that one of the big components was memory, of course, right? So SQL Server controls all behaviors related to memory through a set of LRU algorithms, least recently used, okay? And the -K says, well, let's make allowances for how complicated the execution plan is. And it involves 2 extremely important processes behind the scenes. The first is the Lazywriter, and then the second is the ghost cleanup process, okay? This is the garbage collection in SQL Server's memory. This is how SQL Server keeps things cleaned up and tries to maintain empty space in the cache so you can get work done. And I'm gonna, now, when we talked about RAM before, I only mentioned data cache and plan cache. There's actually many, many caches, lots of caches inside of SQL Server. It's just that the data cache is the biggest by far, usually between 70 and 80% of of memory made available to SQL Server. The plan cache is the next biggest, and it's maybe 20 to 30%. And depending on overall activity inside of the SQL Server system, there are also these other small caches. There's a sort cache, there's hash buckets. Every transaction log has a log buffer. Every extended event has its own little buffer. So there's lots of little tiny caches. However, I'm going to use the plan cache to illustrate how each of these caches are managed. And it kind of goes like this. When an object is loaded into cache, let's say we've got a stored procedure called get order. SQL Server puts 2 bits of information into the metadata. The first is a complexity value. That's the high end of how complex is this relative to everything else. The other is a countdown timer, okay? So every minute, it's guaranteed to happen every minute, but again, SQL Server's processes can invoke the Lazywriter. So Lazywriter wakes up every minute and takes a look. If any of these objects loaded into the plan cache have not been used since the last time it was taking a look, it decrements that countdown timer by 1, okay? So throughout the plan cache. Then it goes away and goes back to sleep. You'll see that there's even a wait statistic called Lazywriter sleep task, right? So it just keeps track of how long it's been asleep. Then Lazywriter wakes up again, either because it was invoked by a SPID that needed memory, or just because 1 minute has passed, and it takes another look and says, okay, has anyone used get order? Nope. So it goes down by 1. Reset user goes down by 1. Proc 11 goes down by 1. Proc 14 now hits 0. Lazywriter goes away. Comes back again in another minute. And we once again go through the same process, but this time Proc 14 is now less than 0. So what happens to Proc 14? Well, if any of you have ever listened to any of my other sessions, I've been saying since about 2002, when I first started doing a lot of public speaking, that it depends. The correct answer to all technical questions is it depends. So what does it depend on? Well, what happens is if you have plenty of memory and there's no memory pressure, SQL Server marks a bit in that little object that says it is ghosted and is now available for ghost cleanup, but it doesn't evict it from the cache. On the other hand, if there's a lot of memory pressure, then the ghost cleanup process, which is always running, says, aha, you've been marked as ghosted and I kick you out of the cache. You're evicted to make room for others. At the same time, Sheldon comes back, the Lazywriter comes back and says, oh, somebody used reset user since the last time. So now I'm going to reset you back up to your countdown timer max so that you have lots more time to stay alive in the cache. So that is what the Lazywriter and the ghost cleanup process do. They actually do the same thing in, say, the data cache and other caches. It's just that in the data cache, there's not one object query code. There's multiple kinds of objects. There's heaps, there's clustered index tables, there's non-clustered indexes. So it has to keep countdown timers on all of those, or even a portion, the last range scan of a date column that's indexed. So it's a lot more complicated in the broad number of objects managed, but in the mechanics, it's exactly the same. So we're out of time. I want to thank you all so much for taking your busy time out of your day. You can read my blogs at SolarWinds.com, thwack.solarwinds.com. I have lots of other sessions of comparable technical depth there. And I hope you'll join me at another session soon in the future.
Thank you, Kevin. It's really amazing session.
Thank you so much. I wish we had more time.
Yeah.
Us too. I was like,
As
no.
always.
Hi, Camille. Yeah.
Hi, guys. Hi. Good evening or good morning.
Good afternoon, good evening, and good night.
Right.
I'll leave it to you. Thank you so much again, Kevin. That was amazing. Randolph will be coming up next. Stay tuned for them. And I think Alpha, this marks the end of your moderator spot. Feel free to hang out, and thank you so much.
Thank you so
for getting
much.
started. It was
Hi, Randolph.
Please don't.
Hey, Daniel.